Two schools, A and B, follow the IB program but have different teaching methods. A research group tested whether the different teaching methods lead to a similar final result. For the test, a group of 8 students were randomly selected from each school. Both samples were given a standardized test at the start of the course, and a prediction for total IB points was made based on that test. This was then compared to the points total at the end of the course. Previous results indicate that both the predictions from the standardized tests and the final IB points can be modeled by a normal distribution. It can be assumed that the standardized test is a valid method for predicting the final IB points, and that variations from the prediction can be explained through the circumstances of the student or school. Question A. Identify a test that might have been used to verify the null hypothesis that the predictions from the standardized test can be modeled by a normal distribution. 1 mark. So can be modeled. So it's about what? It's chi-squared goodness of fit. Chi-squared goodness of fit. It's acceptable, just chi-squared. Question B. State why comparing only the final IB points of the students from the two schools would not be a valid test for the effectiveness of the two different teaching methods. It's clear that because aim is to compare improvement, or because the students may be of different ability in the two schools. The next. The data for school A is shown in the following table. Question C. For each student, the change from the predicted points to the final points F minus P was calculated. Find the mean change and then find the standard deviation of the changes. It was calculated but is not given, so we need find final minus predicted. It's change or difference, and quite easy. It's just this value minus this value, and it's 0.8, negative 2.5, 0.9, negative 2.9, negative 2.1, 3.9, 3.6, negative 0.2. 1, 2, 3, 4, 5, 6, 7, 8. Yes, and then definitely mean can be found, just add them up and divide by 8, but it would be more useful because we also need standard deviation. Use stat, then edit, and L1 is this difference. Our data, L2 it's frequency 111. And then just calc one variable statistics, list one frequency, it's L2, and you can see mean is this value, and notice that it's required just standard deviation for a given sample, and hence it's just this sigma, and this sigma it's like Sn, and a bit larger value it's like Sn minus 1. It's unbiased estimator for the population standard deviation. And the next question there will be to provide a test, and the calculator will ask this larger value Sn minus 1, not this sigma. But here question is just standard deviation of the changes, so just for a given sample, so we need 2.46 to 3 significant figures, and the mean is 0.1875 as exact, maybe written to 3 significant figures. And the next question D. Use a paired t-test to determine whether there is significant evidence that the students in school A have improved their IB points since the start of the course, 4 marks. So we should provide paired t-test. It's just called paired t-test, but we will use usual just t-test, and as data we should consider this difference. And the null hypothesis, just in words, there has been no improvement, and the alternative, that there has been an improvement. In general, we can set a new variable d, which is equal to f minus p, the final minus the previous result, and then the null hypothesis becomes d mean is 0, so no improvement, and alternative there is improvement, so difference final minus predicted is greater than 0. And to provide a test, we use tests, and we need just t-test. And we can use data or stats. Mu 0, it's 0. Why? Because null hypothesis is that there is no improvement. It means that our variable f minus p is 0. So here is 0. Then mean, it's our mean. But notice that here must be as n minus 1. It's unbiased estimator for the population standard deviation. Not this, you can see 2.46, not this value, and that's a bit larger from the calculator. And n is 8, and we need greater because we need there is improvement, so final minus previous is greater than 0, and then just calculate, and you can see the required p-value is here, 0.423 to 3 significant figures. And also since data is provided, we can use data and you remember that L1 it was what our differences. Data, yes, again mu 0 is 0, list L1 greater, calculate, and you can see we get the same p-value. So p-value is 0.423, and the next step is what? We compare these with 1% or 5% or 10% significance level, but here significance level is not given. Why? Definitely it's greater than 1, 5 or 10, so it's not given, because we don't need to compare. But in general, if p-value less than significance level, we accept the alternative hypothesis, or we say that there is sufficient evidence to reject H0. But here definitely it's large, so we can conclude that there is insufficient, there is no sufficient or significant evidence to reject H0. It means that we accept H0, and H0 is no improvement. So there is no significant evidence to reject H0, or in context, significant evidence to reject H0, that the students have improved. The next. The data for school B is shown in the following table. Use an appropriate test to determine whether there is evidence at 5% significance level that the students in school B have improved more than those in school A. So we should compare what two population means. And the null hypothesis becomes, and also can be written in words, so there is no difference between the schools, and the alternative, school B, did better than school A. But in general, for such type of questions, it would be better to emphasize that we compare to population means. What does it mean? It means that, or in other words, we can say that mean, null hypothesis, that mean improvement for all, it's like population, for all students in school A is the same as mean improvement for all students in school B, and the alternative you repeat the same, but for school B to be greater. Or you may set that let mu A be, you may say directly population mean for improvement in school A, or you may say that mean improvement for all students in school A, and then for MB to be the same but for school B, and then null hypothesis, it's no difference, so equal, and the alternative we need mu B to be greater, like this. And how to provide the test? You remember that L1 it's what for school A, and we should enter what this data for school B. And it's this L3, then just tests, and we need two sample t-test. In general, we use t-test when standard deviation is not given, it is estimated. So it's two sample when standard deviations or variances are given, it's that test, but here it's two sample t-test. This one. To sample t-test, and again can be used stats, mean values, standard deviations, and again it's must be assigned -1. But we have data, so data, and a list for school A it's L1, for school B L3, frequencies 1, and we need school B to be greater, so we need this one, better, yes, pulled yes, Yes, and p-value 0.0984. Then we compare with significance level. It is given 5%, and definitely it's greater than 5%. And we accept the null hypothesis, or we say that there is insufficient evidence to reject H0. I repeat the question, whether there is evidence at 5% significance level that the students in school B have improved more than in school A. So if we accept the null hypothesis, it means that in context there is insufficient evidence to suggest that students in school B have improved more than in school A, something like that. But here, so you may write the conclusion in context, but in general we write that there is insufficient evidence to reject H0. It means we accept H0 and H0, no difference. And you may rewrite in context of question if it is required. The next, state why it was important to test that both sets of points were normally distributed, and in total 6 marks. So a situation is the next. When n is large, greater or equal than 30, there is a central limit theorem that says that any sample taken from any distribution when n is large can be assumed to be normally distributed, and when n is small, or less than 30, and if it is not given that the sample is taken from normal, we cannot apply t-test or z-test at all. It doesn't work, because t-test can be applied only if a sample is taken from normal. But when n is large, it doesn't matter, because it can be assumed as normal. So we can say the next: sample is too small for the central limit theorem to be applied, and t-test assumes normal distribution. It means that a sample should be taken from normal distribution. The next, school A also gives each student a score for effort in each subject, This effort score is based on a scale of 1 to 5, where 5 is regarded as outstanding effort. It is claimed that effort put in by a student is an important factor in improving upon their predicted IB points. Question F. Perform a test on the data from school A to show it is reasonable to assume a linear relationship between effort scores and improvements in IB points. You may assume effort scores follow a normal distribution. So we should consider this, and I will consider it as a dependent variable, and I will consider it as x, because the next question is hence find the expected improvement, and we also will need this line of the best fit y on x. So The null hypothesis is that there is no correlation. Correlation coefficient rho is 0, and we check or test whether there is positive, so rho is greater, and just using a calculator. So we use again, it's L1, and we need to enter this. L1, and it's here, it's L5. Then stat and tests, and for linear correlation it's this linear regression test X L5 Y L1. In general, it doesn't matter what is X, what is Y, if you check whether there is a correlation. But here I need equation of a line for the next question, so I choose X to be L5 effort and Y to be improvement. Then we check, we need greater, and calculate, and we get p-value is 0.00157, and again it is not given significance level. Why? Because you can see it's very small, and if it would be, for example, 1% significance level, it's less. So definitely for each significance level it will be less than significance level, so we accept the alternative hypothesis, or there is sufficient evidence to reject the null hypothesis. And I repeat the question to answer in the context of a question. Perform a test to show it is reasonable to assume a linear relationship between. So there is a significant or sufficient evidence over linear correlation and actually it's not given that it's positive, it's just a correlation, but it doesn't matter in general if you test less than 0, then you just consider two situations when it's positive and negative, but significance level just divides by 2. But here if you consider just positive, you can see that it's very small, so definitely we accept the alternative hypothesis. So linear correlation between effort and improvement. So it is reasonable to assume a linear relationship. And the next question is, Hence, find the expected improvement between predicted and final points for an increase of 1 unit in effort grades given your answer in 1 decimal place. So to estimate improvement this on or for given effort, it must be y on x, and y must be this improvement, and that's why we choose effort to be x and y to be this, but for correlation it doesn't matter. And you can see that we get a line of the best fit, a plus bx, and we need change in y for 1 unit in x. But what is it? It's directly gradient. It's gradient by definition, so it's directly b. So it's 6.6. I write to 1 decimal because this data is to 1 decimal. It may be to 3 significant, it doesn't matter. The next. A mathematics teacher in school A claims that the comparison between the two schools is not valid because the sample for school B contained mainly girls and that for school A mainly boys. She believes that girls are likely to show a greater improvement from their predicted points to their final points. She collects more data from other schools, asking them to class their results into 4 categories as shown in the following table. Question G: use an appropriate test to determine whether showing an improvement is independent of gender. 6 marks. So it just tests for independence and how to provide it. And you should remember that chi-square test, it's goodness to fit or independent for independence. The expected frequency must be greater than 5. If it is less or equal than 5, we should combine some columns or rows. And how to check. And actually you can see that it's a small value. It's actually observed data and it's small, so we can suggest that the expected may be less than 5. How to check? Expected can be calculated as total row multiplied by total column divided by grand total. So total column is 9 multiplied total row it's 33, and divided by grand total is just sum. Total sum it's 36 and it's 4.5, and you can see that it's less than 5, so we should combine what? We can combine these 2 columns. And another way how to check, just provide test for independence using given data as usual, and we use what? Matrices, and matrix A we enter given data. How to do that? Matrix edit and just enter data. Then you choose again, not again, stat test and just chi-squared. So for independence we use chi-squared, not goodness to fit, but just chi-squared. Then observed, it's A, and you can see that it is automatically created the expected it's matrix B. Then you perform a test, but we do it to check whether there are expected less than 5, and we need just matrix B, and you can see that for 0.5 there are expected frequencies which are less than 5, but it's the same column. So if we combine these 2 columns, there will be expected greater than 5 as required. So we will consider f minus p just less than 0, and it becomes what, 14, 11, and it's the same, 14, 10, 9, 8. And now we do actually the same, but we need to change our matrix. Edit, it becomes 2 by 3, 2 by 3, and it's 14 now. It's 10, 9, 11, 14, and 8, and then just stat tests chi-squared, and we need again p-value. And you can see that it's very large, and again it is not given significance level, because it definitely will be a greater than significance level. So what there is insufficient evidence to reject H0. There is and also we should write the null hypothesis, improvement, and gender are independent. And remember, the null, it's always for if it's a test for independence, the null hypothesis is that something is independent, and the alternative the same but are not independent. Then p-value, and compare with, as usual, with significance level, but definitely it will be larger. So there is insufficient evidence to reject H0, and in context, if it's required, no significant evidence that gender and improvement are dependent. Because we accept H0, and H0 is what? Are independent. And the last question, H. If you were to repeat the test performed in part E, what is part E? Part E, it's use appropriate test to determine whether there is evidence at 5% significance levels that the students in school B have improved more than those in school A. It's compare two population means. In part E, intending to compare the quality of the teaching between the two schools, suggest two ways in which you might choose your sample to improve the validity of the test. 2 marks. So what is validity? Validity, it's about accuracy. It's does your test actually measure what it is designed to measure? And let's review what is reliability. Reliability, it's about consistency. It's does your test yield consistent result? And for reliability, you should remember test retest, repeat the same process with the same sample at a later time, or parallel forms, second set of questions. And if test retest results, if there is a strong linear correlation, or in other words, results for the same, or for each student, or for if each student gets approximately or very close result, we say that such test is reliable. or just when test results for retest results there is strong positive correlation, we say that such test is reliable. So for validity we can answer the next, definitely to use larger samples or include data from whole school, or take equal number of boys and girls in each sample, or have a similar range of abilities in each sample, or have similar ranges of effort. And that's all for this question.